sklearn, feature extraction, text, hashing vectorizer. Description. Hashing vectorizer is a feature extraction technique used in natural language processing (NLP) to convert text data into numerical vectors that can be used in machine learning models. It utilizes hashing to map words to indices in a fixed-length vector, making it efficient for large datasets and memory-constrained scenarios. Inputs. Text data corpus. This can be a list of strings, each representing a document or text sample. Optional parameters. N features specifies the number of features hash buckets to use. Norm controls the normalization method for feature vectors. Alternate sign if true. Uses alternate signs in hashing to reduce collisions. NGRAM range defines the range of n-grams to consider, e.g. unigrams. Bigrams. Outputs. Feature matrix. A sparse matrix where each row represents a document and each column corresponds to a hashed feature word. Vocabulary in hashing vectorizer. There is no explicit vocabulary maintained. Steps. Tokenization. The input text is split into individual words or tokens, e.g. using whitespace or punctuation as delimiters. Hashing. Each token is hashed using a hash function to generate a unique integer index within a specified n features. Vector representation. A sparse vector is created for each document, where the value at each index corresponding to a hashed feature represents the frequency of that feature in the document. Metrics. Accuracy measures the model's performance on a classification or regression task. Precision indicates the proportion of correctly predicted positive instances. Recall represents the proportion of actual positive instances that were correctly identified. F1 score. A harmonic mean of precision and recall, providing a balanced evaluation metric. Visualization plots. Feature importance plots visualize the importance of different features hashed words in a model's predictions. Confusion matrices display the distribution of correctly and incorrectly classified instances for multi-class problems. Word clouds create visual representations of the most frequent words in the corpus. Fine-tune parameters. N features experiment with different values to control the number of features and potentially affect model performance. Norm. Consider different normalization methods L1, L2, none based on the specific machine learning algorithm being used. NGRAM range. Adjust the range of n-grams to capture different semantic relationships, e.g. unigrams, bigrams, trigrams. Uncertainty methods. Bayesian optimization. Optimize hyperparameters using probabilistic methods to find the optimal combination for the model. Cross-validation. Evaluate model performance with different data splits to assess its generalization ability. Challenges and fixes. Challenge 1. Hash collisions due to the fixed size feature space. Collisions can occur where multiple distinct words hash to the same index, leading to information loss. Sample use case that resulted in challenge 1. When dealing with a large vocabulary or a limited number of features, collisions are more likely to occur. Fixes to challenge 1. Increase n features using a larger feature space can reduce the likelihood of collisions. Choose a robust hash function. Employ hash functions with good distribution properties to minimize collisions. Challenge 2. Loss of word order information. Hashing vectorizer treats words as independent units, disregarding the order in which they appear in the text. Sample use case that resulted in challenge 2. Models that rely on word order, such as recurrent neural networks, may perform poorly when using hashing vectorizer. Fixes to challenge 2. Use n-grams. Incorporate n-gram sequences of words into the feature representation to capture Some word order information. Consider alternative techniques for tasks that require word order. Explore techniques like word embeddings or TF-IDF that preserve positional information.